Hey, is that going, Alexis? Is it?
I think.
Yeah.
Okay, chemistry time. I hope you're right. You're personally responsible for this. Is a little symbol a circle or a square?
Yeah. Videoed everything we
12
just
seconds
said.
now.
12 seconds. Okay, we're burning time. Chemistry time. We're continuing to talk about. Let's just name it. I think the last one I called it was nuclear decay and the nuclear radiation and
Slash
radioactive decay. So this is part 2 of nuclear radiation / radioactive decay. Is that the same title from before?
No, before it was just nuclear radiation.
I think it was actually nuclear radiation / radioactive decay. Someone else has this.
I haven't.
Ni hao. Ni hao. That's how you say hello in Chinese.
Sorry, Kyle.
Ni hao. We have some example problems. The first example problem is the nuclide iodine-125 combines with an electron through electron capture and produces a new nucleus and no other massive particles. What is the equation for this reaction? The second is the first naturally occurring unstable isotope that was isolated polonium-212 was discovered by the Polish scientist Marie Curie and her husband Pierre in 1898. It decays emitting alpha particles. Show this equation. We will do both of those, but first, what part of the table were we on? We'll include these as
We're only on beta.
We're on beta plus, the one we decided before. Well, we started talking about antimatter, didn't we? So we had a table. We had the decay mode, which was, we started with alpha, decay mode. I may have called this something different, but I'm doing this intentionally. I think I called it symbol or name. But the name of what we're naming, like if I just had a column called name, and the names were Peyton, Oak Tree, Dump Truck, these are not names of any specific thing. So I'm being specific now. The name of the what? Decay mode. And actually also the symbol. I'm reconfiguring the whole dang thing, so just sit tight. What was the next column? I'm sorry. Description.
Then charge.
Charge, mass.
Examples.
Mass. And then, well, I'm going to leave off example off the table. We will do them, but I'm going to do them as we go along. So we had alpha mode. We had alpha mode. That's not what it is. Alpha, decay, beta, plus decay is where we were talking. Then we're going to do beta minus. Then we had electron capture. Oh, did we do gamma next?
Yeah.
Sorry. Gamma. Then electron capture.
And then spontaneous fission.
Then spontaneous
In a
fission.
deep voice.
Did I make the deep
No,
voice?
Kyla did. She was like, spontaneous.
There's another one. There's another one, physical science time from last year. Neutron capture. Neutron decay. This one's important because this causes a chain reaction wherein the neutron that comes off of one thing can knock into the next thing and cause that one to then break apart through spontaneous fission. Those neutrons can fly off. The reason this one's important is because it's usually part of the spontaneous fission. Spontaneous fission usually is not. For instance, if uranium-238 undergoes spontaneous fission, which it does, all of the thing's masses add up to 238, but it's not usually 238 half, 160 or 169. It's not, is that right? 238. No, because that would be 119.
I got you.
It's usually not
Lily.
119 and 119. It's usually not even just two things. It's usually two things and then some mess of neutrons. But this is a kind of radioactive decay. Why would it be neutrons? Why is neutrons important? Because what's their, we're starting at the bottom crazily. What's the mass of a neutron? 1 AMU. What's its charge? None. So its description is massive, chargeless particle. And this one, like I said, is important because it can be involved in nuclear chain reactions, where a neutron from one flies off and hits another. Think of it like there's a room in your grandma's house with a lot of porcelain dolls, and you, Mitchell, go in and you yeet one at the ground, and the shards of that one break off and break some other ones. This would be like a nightmare. This sounds like something from a movie nightmare. And the shards of that one break off and break another one, etc., forever until our infinite number of porcelain dolls are all broken. And that process releases energy, just like it does in real life when we have spontaneous nuclear decay. That one this is almost, we'll call this a quasi-side note, because it does exist, and it is just as important as the other ones. I had never mentioned it before because one, I just learned about it today. That's not quite true. I had known about it, but I just learned of its classification along with the other ones today. And then two, because we aren't going to really do a whole lot of math with it like we are with the other ones. This is true of spontaneous fission too. So now that we started from the bottom, we might as well keep going from the bottom. This one was called what?
Spontaneous fission.
Spontaneous fission. I'm putting the name in the description column because I am the ruler of my own ship. Spontaneous fission. Meaning, and I'm also going to put the description in here because once again, I am the ruler of my own gosh darn ship. Spontaneous fission, what does it mean? We've had talked about this one already. What's fission? Breaking apart, like a lip fissure that you might have, remember, when your lip splits. And then spontaneous means?
Random.
Yeah, we're somewhere between random and immediate and all on its own. So let's put that it suddenly breaks up. You've been there. A weak laughter. A weak laughter emanates from the high schoolers. Charge? Well, I don't know. It has a charge and it has a mass, but it's different every time. Or that's not strictly speaking to. There would be times when it was the same. But the charge and mass are unknown. They can't be known until after it happens. What it amounts to, though, is neutron release. This is where this becomes knowable, is because the ones that actually matter about it are when the neutrons go on and break the next dude up. And those neutrons go on and break the next dude up. And then whatever isotopes are remaining after that kind of randomly then usually decay into more stable elements anyway. So we're left with, after spontaneous fission, or after isotope that undergoes spontaneous fission, we're left with a radioactive blob made of other isotopes besides the one that started out. And some of the isotopes that did start out because they only go off of half-life. You remember half-life? Yeah, half-life, here's a side note, where the side notes are getting their own side notes. Side notes, let's start with half-life. Because remember, all of this is effectively based off of random chance. The way we measure it is half-life, which is the length of time. So what kind of units would we use to measure half-life? Length of time. Time units. Years, seconds, milliseconds, sometimes billions of years. It depends on the isotope. But every isotope has its own half-life. So if this is happening randomly, how come each isotope has a known half-life? Sometimes 10 decimal places of known half-life. How can that be?
What?
The question is, how can, if these all decay randomly, which they do, including spontaneous fission, all of them decay at a random rate for each individual isotope, how can we know the time of one half-life? Length of time it takes to, what? This is the answer to that question and the answer to the end of the sentence.
Decay.
Takes,
the isotope to
for half to decay, decay, here's the key, on average. That's how we can know it so exactly, is because we're not really measuring, oops, I put the period on the board. We're not really measuring how long it takes a specific example of that isotope. We're not thinking about how long it takes for one atom to decay. We're thinking about the time it takes for a whole blob of it, even if this little eraser was made of a radioactive substance, this is still billions or trillions or quadrillions of atoms. So it's still an enormous amount of atoms, and the amount it would take for half of them, on average, would end up being the same from this eraser to this eraser, because they have the same mass, because just it averages out over billions and billions and billions of times. Does that kind of make sense?
Yeah.
So we can get it very precise. We can know its half-life very precisely, even if each individual atom, it's a complete crapshoot, heads or tails. It's one way or the other. It does or does not decay.
A banana is like a week, so it's half-life.
Yeah, we do even sometimes use half-life on other things. As we're talking about it now, you should be aware that bananas don't have a half-life. Although it's interesting you chose bananas, because bananas are high in potassium. Potassium-40 is a radioactive isotope that's really in bananas a lot. But things that decay like biologically, like a corpse or a banana, which is a corpse, don't at me. It's one of my founding principles is the banana is a corpse. It's dead. It might be still some of the cells are alive, but the thing itself is dead. Anyhow, Biological decay is not what we're talking about. We're talking about radioactive decay, where a isotope decays into its daughter isotopes. And we'll talk about what that means. We have a lot of stuff to cover. It just piles up and up and up. Anyhow, this is how long it takes. It's a length of time measured in something like seconds, years, centuries. Okay, I'm just going to give up spelling centuries so they're in a room. Just put a Y. This is a way of measuring all of these. This applies to all of them. Okay, we happen to talk about it after spontaneous fission, but it applies to all of them. Let's move up to electron capture. Electron capture. Where do the electrons normally hang out? And why is this one important?
In the electron cloud.
In the electron cloud, outside of the nucleus. But what happens is sometimes in a very large nucleus, the electromagnetic attraction between the protons in the nucleus and the electrons in the lowest energy level are overcome their dynamic repulsion, and that electron zooms in and it changes. Electron would change a what to a what in the nucleus? A proton to a neutron. So it has a charge of -1, a mass of none, and it changes in the nucleus, it changes a proton into a neutron. So its net effect on the nucleus is what? What happens to the atomic number? Let me rephrase it. What would happen to the atomic number if a proton changes to a neutron? The atomic number goes down. I'm going to make this a little smaller so I can write that. Proton to neutron. And so the atomic number goes down 1. And the atomic mass does what? Stays the same. Do my little symbols make sense? I mean, this is kind of like shorthand. The atomic number, yeah? Hashtag arrow 1. That's not what we're talking about. The atomic number goes down 1. So if it was, I meant to bring my iPad up here so I could tell you a specific one that actually does this. Stand by. Okay, back with the iPad. Here is a specific example of electron capture. Was yours titled examples in this column?
Yeah.
Do you have room to write this example?
I wrote what you just wrote.
Okay, and that would be, I mean, that's kind of more of an explanation. But here's a specific example which I will do. I'm going to institute this. This is going to be the examples box, and I'm going to erase it each time. How can you get the information that was in here after I erase it? Watch the video. And also you could write it in your notebook. So here's the example of, for electron capture, we have thallium-204. Thallium-204 plus an electron produces. The first example we've done actually happens to be an exception. Why is this one exceptional, those of you who do physical science? What's different about this one from how we write all the other ones? In this one, we put the decay mode, electron capture, on the reactant side because it combines with the nucleus. In all the other ones, it'll be a thing that is released. But in this one, we put it on the side. So anyway, thallium-204 combines with electrons, we call it electron capture, to produce, well, if the atomic number went down 1, what is it now? It's not
3.
Nope, that's the mass. So the mass changed?
Oh.
No.
So it's still 204, but now thallium is number 81, so it becomes instead mercury 204. How did I find that this one, thallium, became mercury? Well, I look at the periodic table, and thallium is number 81. So if the atomic number decreased 1, it would now be number 80, which is mercury. So do I have to write 80? Some people do. Some people write the 81 down here and 80 down here, but I didn't have to, and how come?
Because we know.
Yeah, because mercury always has 80 protons, and everything with 80 protons is...
Bless me.
God bless you, Peyton. Sounded like a threat because of the noise you had made before it. Okay, so that's electron capture, and just to save time, we're going to move on to the next one now. So now we're on to gamma. And by the BT dub, what was gamma? We talked about this already, but gamma is a kind of what?
Ray.
Yes. It's a kind of, yeah, it's energy. It's only energy. All of these release some energy, but this one is only energy. Charge? None. Mass? None. Change then? Yeah, no change in anything. Usually, the gamma will be part of something else. So it'll say something like Let me find an example that does this. It'll say something like substance or isotope blah 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 X undergoes alpha decay and gamma. And the gamma doesn't change it at all, you just include it in the daughter product. Okay, here's one. Ooh, this was a good one. I didn't even pick this on purpose, but it is a really good one because of what we just did. So we have ruthenium, I believe. Yeah, ruthenium, 97, undergoes electron capture and gamma emission. So we do it like this. So first of all, let's go back to electron capture. The reason I like this one is because now we get to practice the one we just did too. So now, what's the mass going to be?
97.
Still 97. So now instead of ruthenium, which is number 44, it's going to be technetium, which is number 43, and a gamma ray. And that little gamma, does that change it at all? Not numerically, but we still have to show it because gamma rays were released. And here's a good time to notice, this is not just an example for this one, this is for everything. These together, I used this word before, but now we're going to specifically name them. What do we call these things? No. No? In chemical equations we do, but in these are the parent, and these are the daughter.
Always have to be daughter.
It's always got to be daughter.
Well, that's why I said mother.
Yeah, I mean, that would make sense.
That's what I said.
That would make sense, but it is.
Seems to radioactive decay is almost.
A little sexist.
Okay, next we're going to go on to beta minus. So beta minus, we had done beta plus. What was beta plus?
It was.
We didn't have.
We just had E plus next.
Yeah, which is what?
Positive.
A positron, which is a kind of what? Antimatter. And we also had that alpha was a helium nucleus. So this is all from the previous video. We'll do examples
No, we
of them
didn't
still.
do the description, the charge, the mass, or the example.
Yeah, stuff you just scribbled out. We didn't.
No, but for alpha we did, right?
Yeah, but for alpha.
And we'll do examples for both, I'm sorry.
We did for alpha?
We did.
Yeah, we did.
Not examples, but we
didn't do
did.
it.
No, no.
Okay, we'll just fill out the whole table today. I guess whatever I do before is useless. Anyway,
Might as well.
but we did talk about that it was a positron. So what would beta minus decay be, you reckon? E minus, which is a or and? Electron. I was looking in the wrong spot, wasn't I, Lily? I was barking up the wrong tree because I should have been looking at pilot. Charge on an electron? Same as the charge on electron capture. Minus mass?
0.
0. Now what's the difference? What's the dadgum difference between electron capture and beta minus decay? They're both nuclear decay, that's not what I asked. What's the difference?
In electron capture, the nucleus is capturing an electron.
Okay.
It changes the proton.
Yes. In electron capture, the electron is being received by the nucleus, changing a proton into a neutron. In beta minus decay, an electron is leaving the nucleus. So I shouldn't have drawn arrows to the same spot because I'm doing contrast. The nucleus is absorbing an electron in electron capture, and the nucleus is releasing an electron in beta minus decay. We'll show that in our equation as instead of being on the parent side, it'll be on the daughter side. And if an electron now is leaving, what is changing?
Plus 1 to the atomic number.
Right. So, but is a proton changing into a neutron?
No.
No, a neutron is changing into a proton. And so the atomic number does what now?
Goes up 1.
Goes up 1, and the mass number does what? Stays the same. Okay, so here's an example. Niobium-94 undergoes beta minus decay and gamma radiation, or gamma ray release. It doesn't matter how you phrase it. So what do? We have niobium-94. It's going to undergo beta minus and gamma.
So draw our arrow.
Draw our arrow. What was the parent here? No one remembers what its name is.
No.
Niobium.
Yeah.
Say it. Niobium-94 is the parent. What are the daughter products then? Well, what's going to be released? We just said.
It's going to be plus 1 on the atomic.
Well, yeah, but what? Okay, sure, we can do that one first.
Where the heck is
How's the mass going to change?
No, it's not.
No change in mass. It's still 94. But instead of niobium,
Where's my plan B?
Where's my boy NB? Instead of niobium, it's going to be what?
Well, I gotta find him first.
41.
Whoever finds him first. It's gonna be molybdenum.
Molybdenum. Which, we had actually, interestingly, we had just talked about. What do you think the root word for molybdenum is? It's the same as mollify, which is soft. Yeah. Anyway, so molybdenum 94. And
Plus an electron.
Yep, and an electron, or we could put beta minus, doesn't matter either way. Or and, I said one other one, gamma, and gamma. Are they always gamma?
Nope.
No, but in this case it was. So this can be either beta minus or an electron. Those are interchangeable in this. Okay, so then for beta plus, it was a positron we said, which is antimatter. What's the charge of that going to be? Positive. Mass? 0. Boy, we have a real roll going down here, don't we? But, okay, so if the mass is 0 and the charge is +1, this is going to be releasing what?
A positive thing.
Not a proton.
A positron.
No, a positron, which we write as E+. It releases an E+ from the nucleus. So in this case, a neutron doesn't change into a proton, it's the other way around. A proton changes into a neutron. You see, I have to conceptually understand that a positive charge is leaving the nucleus. So a proton, which has a positive charge, gets rid of that, and it becomes a neutron.
Yes.
What causes that to happen? What force of the universe causes a proton to lose its positive charge and become a neutron? The weak force. Yeah, good. The weak nuclear force governs that interaction. There's only 4. So then, would the atomic number change?
Nope.
Try again. Yep.
The
How?
atomic mass will change.
How will the
It'll
number
go
down 1? The mass will.
Answer will not change.
The mass will not change.
Yes.
The mass will not change. Let's find a new example for us. We're really flying through this. I know it's kind of complicated. I appreciate you bearing with me. Hopefully this one's got me. It doesn't. Most of them are stable. Oh, nope. I don't mean most of the isotopes are stable. It's just that I was the one I picked. Most of the isotopes are stable, which is kind of rare. Golly, the other one I picked was kind of stable. What I'm doing is on Wikipedia, and I'm just randomly picking elements from the periodic table and then looking at their isotopes. Technetium is the one I clicked, and this one does not have it. It does have only radioactive isotopes, but it doesn't have beta plus. Apparently, magnesium has only stable isotopes. That's
One nice
some trivia.
positron.
Oxygen has only stable isotopes. We're having a hard time. I'm gonna have to cut this video. Gosh, dang it.
Uranium, it's got all the things.
I probably could. If I wasn't such a stubborn person, I'd probably just type in beta plus decay and look at examples.
This is how I'm gonna do it, because I'm capturing this shit.
This is how I'm going to do it. Bismuth, come on, Bismuth, you got it. Yes, Bismuth has one. Bismuth 207 undergoes. Bismuth 207 undergoes beta plus decay. So Bismuth 207 undergoes, that's how you pronounce the arrow. In chemistry, we have a different pronunciation for this arrow, but in nuclear equations, we call this produces or decays into. Bismuth 207 undergoes, I said beta
Same.
plus, so it's
207.
so E plus, and then it's gonna have the same atomic mass,
And then it
207,
turns into lead.
and then instead of
Oh wait, no, it goes up.
instead of bismuth, it's going to be
polonium.
polonium 207. Nice. Okay, alpha. Oh, sorry.
I know, it's okay. Just when did this after the 207?
It's polonium, PO. Capital PO.
That's all I
So,
needed.
okay, charge on the alpha. We had said it was a helium nucleus. So the charge is +2. The mass?
4.
4. So then, the proton doesn't change into neutron or anything like this. So this helium nucleus just leaves the atom as one big lump. And so what happens to its atomic number?
It will go down 4.
Go down how much? The number?
2.
2. The number goes down 2, and the mass goes
Up 4.
Down.
down 4 because it's leaving the nucleus. These ones, I know exactly where to look on the table to find these because mostly, for the most part, only very heavy elements undergo this. So we have meitnerium, 274. Meitnerium 274, which is named after Lise Meitner, a German, female German chemist from the early 1900s. Very important person. Anyway, named after her, Meitnerium 274 undergoes alpha decay. So undergoes, we can write this in a couple different ways, and I'm going to write both. Alpha, just the Greek letter alpha, plus, okay, now look, its mass goes down 4, so now what's its new mass? 270. And its atomic number goes down 2. So instead of Meitnerium, which is number 109, it is now Bohrium, named after, can you imagine? The same person as the Bohr modeled the atom, Niels Bohr, nuclear physicist in the 1930s and 40s, I think. Bohrium 270. You can also write it, this is the exact same thing, and either is acceptable to me, unless, sometimes just for your practice, the problem will specify, write it as a helium nucleus, or it'll say write it as an alpha particle, just so you have the practice. You can also write it as a helium nucleus. And why might this be better?
It shows you every part of
Yeah, it shows you, and in fact, if you write the Meitnerium as, what was it, 109? Yeah. If you write the Meitnerium as 109, 274 minus 4, that's where the 4 is, it's just 270. 109 minus 2 is 107, and then you just look up what 107 is.
And you're done.
Where's 107? Boring. Dangerous. Not blocked by paper, right?
Yeah.
Slightly less dangerous.
It's real cool.
But blocked by,
Paper's small.
usually some metal foil will block it, any kind of metal, because these get absorbed. This gets absorbed easily by any kind of matter because it's matter. Matter can't go through matter. That's one of the things of the universe. You learn that very early. My 15-month-old son is learning that because when he tries to go through the drawer, instead he bonks his head on it because matter doesn't go through matter. So it's real easy for alpha particle to get blocked. The beta particle is small matter, though. So in the same way that, like, if there's a hole in your screen door, a fly can buzz in. It's still matter, and it's going through matter, right? It's going through a hole. This takes slightly more to block. Gamma, several feet of concrete, several meters of concrete, or a few meters of lead, but it takes quite a bit more because gamma is just light. In fact, it has a much shorter wavelength than normal light, so it can penetrate matter better. Electron capture would be the same as beta minus. It does the same effect over here, but it would be penetrated the same. And in fact, we don't really worry about this because it's an absorption rather than a release. Spontaneous fission, it depends. Basically, it's just this. These two really only occur with very heavy elements, and we're more worried about them for nuclear reactors. These are the ones that tend to be emitted by matter that could be damaging. In fact, when someone says radiation, they probably mean either, if it's a scientist, they might mean electromagnetic radiation, like microwaves or radio waves, but probably, in layman's terms, these are what we would call radiation. I'm going to put that in quotes. It's gross to talk, or sad to talk, I don't know, it's either sad or gross or both to talk about. When someone is having radiation therapy, they mean one of these, certainly.
So you cry and then puke when you talk about
Gross. Mitch, come on. Questions about any of this?
Why is electron capture the same as beta minus? When beta minus increases it that number, and electron capture
Did I mess up?
decreases it.
Oh, it's the same as beta plus. I mean that these would have the same effect on how they penetrate matter.
Okay.
These have different effects as far as the results. But that reminds me of something interesting I was going to point out. You notice beta plus causes the atomic number to go down. Beta minus causes the number to. Electron capture causes the number to. Okay, so here's a problem that continually happens in physics. A man named Benjamin Franklin, you've heard of him. He was old back then, and he's old now, and he's dead now. Discovered electricity. I'm putting it in quotes. I have a marker, so it doesn't look like that. But he discovered electricity. He, at the time, and this might be apocryphal, it might have been someone else who did this, but he ascribed the electron as having a negative charge. But it would be so much easier for so many parts of chemistry if the electron we consider to have a positive charge. It wouldn't really matter. What really matters is that opposites attract. We might as well say the proton has a negative charge, the electron has a positive charge. It wouldn't change anything the way it works, except that it's customary now to call it a negative. In fact, if you look at circuits, we call the negative end of the battery the one the electron is actually flowing away from. So everything's backwards. Same with this. Beta minus means the atomic number goes up. Everything is upside down. What about when we were talking about valence electrons? If it gains valence electrons, what happens to its charge? It goes down. It gets a negative charge. So everything's upside down. Like anytime we're talking about electrons, the changes in things become reversed. You can kind of use that as a cheat code. Like, you know, based on my new cheat code, that if it undergoes beta plus decay, its atomic number is going to go down. Anyway, cheat codes. Spitting cheat codes up here. Myself. Okay, I have to cut that part too. Anything else? Oh, we were going to do these specific ones on the board. So it says iodine 125 combines with an electron through electron capture. Let's use the whole board for this. Perfect. Iodine 125 undergoes electron capture. I've distilled. If you're watching the video, you can rewind to when I actually read this. But I'm distilling it to iodine 125 undergoes electron capture. So what do I write first?
Right. Iodine 125.
So I'm going to write 125I, right? Don't pronounce it that way. Do as Kyla said, pronounce it iodine 125. I'm just telling you what to write. Iodine 125 undergoes, it says, so there's our arrow, undergoes electron capture, but wait.
Uh-oh.
Where does the electron go in electron capture?
Left side of the arrow.
It goes on the parent side. So plus an electron. What's it going to produce? Well, according to our chart, which I've conveniently erased. Oh no, it's still here. The atomic number goes down 1, so 124. What if I hadn't erased, or what if I had erased the chart?
That's not the atomic number.
You know that it's the opposite of...
Oh, yeah, sorry.
He was doing it so we...
The mass number still
I was
wasn't
doing it.
I was doing that on purpose because I'm not stupid.
Because he wanted us to see his mistake.
Not my
Technically,
mistake.
I counted and called it out.
Thank you.
Then it's going to be tellurium.
Tellurium.
It'll be tellurium. Tellurium. The atomic number went down. It says no other massive products. What does that mean? Why does it specify no other massive products?
Because those are the ones that will change.
Well, it was probably released also, though.
A gamma.
Maybe a gamma. It doesn't say that, though. It would usually say gamma, but some other kind of energy, probably. This process always releases energy. Okay, so that was the first practice problem. The next one says, we're talking about polonium-212, and it decays emitting alpha particles. So polonium-212 undergoes, right, alpha decay. How do I write alpha decay? Let's do it two different ways. So yeah, Lily wants to just use the alpha, which is fine. Plus, well, it's alpha, and being released from the nucleus is a object with a mass of 4 AMU and a charge of 2 being released. So that this is going to go down 4 to be 208. And then if we're releasing a positive 2 charge, what's going to happen? Instead of polonium, now it'll be lead. The half-life of polonium-212, where did I put my iPad? Oh, it's behind here. Just to bring it back to half-life before we finish. The half-life of polonium-212, I'm going to tell you once I look it up. Which one's polonium? 84? Clear over here, that one. Polonium. Yep, the half-life of polonium-212, it'll tell me on wikipedia.org. Not a sponsor, but I do highly recommend it. Not even on the dang chart. Thanks, Wikipedia. Not a sponsor. Don't recommend it anymore because they should have just told me. I wonder if the problem is wrong, because Wikipedia only talks about polonium-210, polonium-208, and polonium-209. Maybe there's no such thing as polonium-212. Oh, some happy music for the video. Some royalty-free happy music. Well, let's pretend they were talking about polonium-210. Maybe I made a typographical error. The half-life of polonium-210 is 138 days. So what that means is if Marie and Pierre, just call them Paul, just disrespect them by calling them the wrong name. If Marie and Pierre Curie had a lump of polonium-210 in 38 days, a little more than 3 months, no, a little more than 4 months, half of that lump would now be lead-208, which is not a radioactive isotope, it's stable. And so they could measure that. And then over time, in another 138 days, how much of it would be lead? No, about the whole thing.
Another quarter.
Another quarter, because it'd be half of what was still polonium is now lead. So now it'd be 3/4 lead and 1/4 polonium. And then in another 4 months, it would be,
Another 8.
yeah, it'd be an 1/8 polonium and 7/8 lead. Yeah. Then a 16, etc. It just halves every time. Questions? Peyton, question?
Nope.
Got it.
Alexis,
I'm
questions?
not reading it out.
Can